So the warbler example was an example of a discrete random variable. Now we're going to talk about a continuous random variable. And again, remember, this is where any uncountable number of values can take place for a distribution of data. We'll calculate and we'll characterize the distribution by a probability density function. And we can think about, because we're dealing with probabilities, if we draw a curve of the distribution, the total area under the curve must be 1, and your probability that y is between some value a and b is the area under the curve between a and b. And so we'll talk about the normal distribution a lot because that comes up so often in statistics. But other examples include the chi-square, the uniform, the beta, and the gamma distribution. All of these are examples of continuous random variables. So as an example, here's the normal, the bell-shaped curve, are common continuous random variables. But other ones include the exponential, or we have some, say, a lot of people talk about the exponential distribution when we talk about exponential growth rate or exponential decay rates. Or the uniform distribution. I think about like rolling a die. Any die roll is equal as the next die roll, as long as we assume that we have a non-weighted die and a fair die to play with. So here's the normal distribution. It's bell-shaped. It's important because it's the basis for inference that we make in lots of statistics. Any normal distribution is completely specified by two numbers, the mean value mu and the standard deviation value sigma. And so the mean value mu is the center of the distribution. The standard deviation value sigma measures the spread of the distribution. And so what we see here is this graph on the right. We see a pretty narrow or smaller standard deviation in this distribution compared to the graph on the left, which has a wider or a larger standard deviation. Here's an example of the normal distribution in real life. And so this is a set of weights used at some gym somewhere in the world. And what you can see here is that when people go, you can see the wear and tear on the weights. When people go to lift weights, they tend to choose, on average, mostly from around that 50 pound, 60 pound, 70 pound area. That's where most of the wear and tear has been on this set of weights. There hasn't been a lot of wear and tear on the low weights, the 15, 20 pounds, and there hasn't been a lot of wear and tear on the higher weights. And so when most people go to the gym, they're putting the pin in these middle weights. So we can think about this might be a normal distribution that we might see in real life. The empirical rule tells us something about the normal distribution that's really important. So we can think about mu plus or minus sigma, that is the population mean plus or minus the population standard deviation, contains about 68% of the observations if the data are distributed normally. Mu plus or minus 2 times sigma has about 95% of the observations, and mu plus or minus 3 times sigma has almost all of the observations. And so when someone says you were 3 standard deviations above the norm, that means you were much higher than the mean, and that might be a love letter from a statistician. So here's what that looks like in action. Say our mean values are centered around 0. 68% of the data are going to be within plus or minus 1 of the mean, or 1 standard deviation of the mean. Within 2 standard deviations of the mean, you'll have 95% of data. Within 3 standard deviations, it turns out to be 99.7% of the data. So this is the empirical rule for the normal distribution. There's a special normal distribution called the standard normal distribution, and this is when the normal distribution has a mean of 0 and a standard deviation of 1. And we write that with a capital N, 0, 1. Mean is 0, standard deviation is 1. This is really the foundation of the z-score that we'll look at much more in depth. We're going to step through some calculations looking at a variety of wheat. And we know that its mean yield is mu of 63 bushels per acre, and its standard deviation sigma is 47 bushels per acre. Now that represents what we know about this population of wheat when we've harvested it for, let's say, decades. But we have a researcher that collected some data on 50 plots. They calculated a mean of 74 bushels per acre. And we want to find out, is that unusually large? So we know that the population mean is 63 bushels per acre. But we collected quite a few plots, 50 plots, and we had a mean of 74. And so our calculation is going to ask, is that unusually large?